We're both located on second floor of Cougar. Our phone numbers and our email addresses are there. Also, the TAs for the course, we have not made any assignments yet. We know who the people will be that will be working with the laboratories, but we have not made time assignments for the courses. Dagon, do you want to make any comments before we get started?
No, go ahead. Our office is just across door from each other, so it's very convenient.
And we haven't both set up office hours yet. We will let you know next next lecture, when our office hours are set up as well. There are 4 laboratory sections for the course. Section E, if anybody tried to register for that, has been closed. So we'll try to work everybody into 4 laboratories. The labs will all meet in room 2046 of Cougar, and the labs will start this week. And homework assignment 1, which is due on this Friday, was posted earlier this morning. So that's a bit of a background. Does anybody have any questions before we start? Catalog description of the course, integrated electronics. We're going to talk about semiconductor technology for integrated circuits. We're going to talk about modeling of integrated devices, including diodes, BJTs, and MOSFETs. We'll talk about physical layout, circuit simulation, and then we'll look at both digital and analog building blocks that are used to build integrated circuits today. Couple of comments about the electronics industry. Almost all electronic circuits are, at the most fundamental level, an interconnection of transistors and some passive components, such as resistors, capacitors, and inductors. But by far, the dominant component in electronic systems today are the transistors. There are orders of magnitude more transistors being used today than there are resistors and capacitors and inductors in our integrated circuits or electronic systems. For many years, electronic systems involved placing a large number of discrete transistors along with passive components on a printed circuit board. If you open up some older equipment, you'll see a printed circuit board with lots of resistors, lots of capacitors, and a few transistors. Today, most electronic systems will not include any discrete transistors, but often billions of transistors grouped together in a few clusters called integrated circuits. In this course, emphasis is going to be placed on developing an understanding of how the transistors operate and how they can be connected together to perform useful functions and to perform integrated circuits. In order to discuss the operation of transistors, if you look in the past, we talked about transistors as kind of a key building block, and we didn't worry too much about where they came from. We said, here's a device with these characteristics. But today, since we no longer use discrete transistors hardly at all, it's necessary to have some understanding of the fabrication technology, because that fabrication technology gives us a lot of insight in regard to the properties of the transistors, their potential, and their limitations. So we'll spend a fair amount of time talking about fabrication technology as well. I struggle with how to approach the discussion of electronics today. We have about 4 things that have to come together to understand how a circuit works. We have to understand the fabrication technology. We have to use CAD tools or understand the CAD tools. We have to have device models so we understand how the transistors themselves work and the other components. And then we have to look at circuit structures and design. And I can talk about any one of these 4, or Dr. Cheng can talk about any one of these 4 areas, but without knowledge of the other 3 areas, it's going to be difficult to see the big picture, see how this all fits together. So what I'm going to do is take the approach that for about the first 4 weeks, we're going to bounce back and forth between these 4 parts of the puzzle. And it's fair to ask the question, how does this all fit together? We won't tell you how it all fits together initially. But at the end of about 4 weeks, you should hopefully see how these things coalesce together. Then it makes sense in regard to what we're talking about and why. Okay. So take it on faith for a period of time that we may not have all the parts of the puzzle together, but we should have an understanding of how these fit together in about a month. Here's a more detailed description of the topical coverage. Semiconductor processes, device models, layout, simulation and verification, basic digital building blocks, behavioral design and synthesis, and the basic analog blocks. And this is about the sequence at which we're going to cover these topics. With one exception, or with a couple of exceptions. We're going to start talking about device models early this week. We will still be talking about device models the last week of the semester. We will talk about device models throughout the whole semester, and our device models will continually evolve and get better, but we'll take a just-in-time approach to discussing device models. If you look at device modeling of the MOS transistor, if you look at the number of research papers that are published on the operation and the modeling of the transistor, there will be well over 1,000 papers published this year on the modeling of the transistor. And there have been a similar number of papers published in 2017 and 2016 and 2015 and so forth every year in the past. There are thousands of papers published on how the transistor operates. Do you think we really understand how it operates today? Well, we wouldn't be publishing all these papers if we really understood everything about how the transistor operates. But we know a lot about how the transistor operates. Here's an indication of the relative time we'll spend on the different topics in the course. The designated textbook for the course is CMOS VLSI Design by Westy and Harris, the 2011 edition. It's actually the 4th edition of this textbook. I believe this textbook is also being used for 465, at least at the current time. I'm assuming that will be the case for those that take 465 in the fall, but I can't guarantee it. There will also be extensive course notes presented. There will probably be over 1,800 PowerPoint slides that will be made available as well. We will make no attempt to follow this textbook on a section by section or a chapter by chapter basis, but much of the material we talk about will be covered in the textbook as well. Grading policy for the course: there will be 3 exams. There will be one final. All the exams are weighted the same. We will take attendance starting on Wednesday, and attendance and quizzes, if we should choose to have quizzes, will be worth 100 points. There will be a design project as well, and that'll be 100 points. A letter grade will be assigned based upon the total accumulated points, and grade range will be determined based upon the overall performance of the class. If you look at the total number of points one could accumulate, then there are 400 points for exams and 400 points for other materials. I don't like to take attendance. I don't feel anybody should be forced to do anything. But my experience has been that in those semesters where I choose not to take attendance, the overall average performance of the class is significantly different than it is when we take attendance. So that's the reason the attendance is there. I said the letter grade will be assigned based upon the total accumulated points, and grade ranks will be determined based upon the overall performance of the class. So everybody in the class could get an A. And if you convince myself and Dr. Chin that you learned the material very well, you'll all get A's. If you convince us that you don't learn hardly any of the material, you'll all get F's. Actually, it's never happened at either extreme. Usually a reasonable number of students do a very good job with material, and oftentimes a few students don't do very well with the material. So here was the breakdown of the grades that were assigned for the previous 3 semesters. And I only give this to you for information purposes. This is how the grade breaks were determined in the fall of 16, in the spring of 17, and the fall of 17. Okay. A few comments about studying for this course. We're going to have a lot of detail that's discussed here. By focusing on the broad concepts, I think you'll find that the details are easy to grasp. If you try to focus on the details rather than the broad concepts, I think you'll find this material very difficult. So it's essential you understand the big picture. Read the textbook as a support document, even when lecture material is not concentrating on specific details presented in the book. There will be a lot of homework problems assigned. Discussing homework problems with others on occasion is not forbidden. However, time is best spent solving problems yourself. If you look, you can probably find solutions to some of the homework problems that we've given in the past. Some of the problems will be repeated. Homework assignment 1 is identical to homework assignment 1 from the last semester. If you spend time looking up old homework solutions, you may accumulate points that are allocated to homework. You likely will not do well in the course. So I encourage you to not try to find solutions for problems that might be available. Homework problems, that's not a way to really learn this material. So the value derived from homework is not the grade, but rather the learning process that I think is associated with doing the problems. We're expected to provide an attendance and access policy. So I'll try to outline it now. Participation in all class functions and provisions for special circumstances, including special needs, will be in accord with ISU policy. Attendance of any classes or laboratories, turning in of homework, or taking any exams or quizzes is optional. Don't have to do anything. However, grade will be assigned in accord with the grading policy we described. So if you choose to skip 2 exams, that's fine. If you choose to skip the labs, that's fine. Oh, but there's one other caveat. All laboratory reports must be completed to pass the course. So let's see, anything else here? Oh, there will also be milestones set up in the laboratories. And there'll be 2 or 3 milestones that the instructor in the laboratory will give you. And you will be asked to demonstrate something to the laboratory instructor, and they'll check off the milestones. We do this to try to keep track of exactly how everybody's progressing in the laboratory. We will expect the milestones to be checked off before you turn in the laboratory report. In the event that you choose to finish the laboratory report after the class, the TAs will be able to check off milestones in other sections. So should that be an issue, we can provide provisions for that. Laboratory safety. In the laboratory, you'll be using electronic equipment that can cause serious harm or injuries or even death if inappropriately used. One way to cause a real problem is to stick your fingers into the mains of a power supply. However, if used in an appropriate way, the risk of harm in the laboratory here is very low. However, safety is still important. Your TA will go through a laboratory safety procedure and ask you to certify that you have participated in the laboratory safety training. One thing that we oftentimes ask you to do is be familiar with the operation of all the equipment. We used to have a requirement that you're supposed to read the manuals for all the equipment. I checked the number of pages in the manuals for the equipment in our laboratory. There's probably 3,000 or 4,000 pages of documentation. My guess is there's nobody in the laboratory that's read all those pages in the operator's manual. And that doesn't include the soft documentation that's in embedded menus on the equipment. Be conscientious and careful with the equipment in the laboratory for your safety and for the safety of others. I think a guiding principle is use common sense when you're working with this equipment. If you have any questions on how it operates, either check with the manual or check with the laboratory instructor. Homework assignments are due at the beginning of the class period on the assigned due date. So assignment 1 is due at the beginning of the period on Friday of this week. Late homework will be accepted without penalty up until 5 p.m. on the designated due date. Homework submitted after 5 p.m. will not be graded without a valid written excuse. Laboratory reports are due at the beginning of the period when the next laboratory experiment is scheduled. We ask you to provide a hard copy to the TA and then a PDF copy to both the TA and to the instructors, of course. The name of the PDF file should have W330 Lab, so we know what the email is about, and then your name on the laboratory assignment. You can read the rest of the material later. Oh, the final project report is due on Friday, April 27th. That's the Friday of Dead Week. There will be a design project that will focus on the design of an integrated circuit. It will be assigned at about week 10 or week 11 in the course. You'll have the opportunity to have that circuit fabricated through the Moses service. Fabrication of the circuit will not take place this semester, however. So if you choose to have it fabricated, it will be fabricated probably sometime over the summer and can be evaluated in the fall. The cost of this fabrication, if you had to pay for it yourself, would be several $1,000s. It's a fantastic opportunity to be able to fabricate a circuit. Although I can't guarantee it, if somebody fabricated a circuit that had decent functionality, it's oftentimes a ticket to a job. Interviewers are oftentimes very impressed if you can successfully design and fabricate and test an IC. Here are a group of reference texts. I'll let you go through these again at your own leisure. Oh, cell phones. The communication policy, of course, what should we do? Does everybody have a cell phone or a smartphone? I haven't heard it ring yet. What should we do? Well, use them. If you look at what drives the microelectronics industry, it's the cell phones. Asking people to turn off their cell phones is like asking people not to buy the products that we try to design and sell. So use them. Hearing ring means business opportunities, means jobs, and so forth. However, if they ring in the classroom, please step outside the room to carry on your conversations. Let's talk a little bit about the semiconductor industry, how big it is and how it compares to other industries. Does anybody have any idea how big the semiconductor industry is? I haven't seen the final figures for 2017, but it was just under $300 billion in 2017. That's just a number, isn't it? Is that a big number? Yeah, it's a pretty big number. Notice that there's been a steady growth in the semiconductor industry over the last 2 decades, and this growth will continue. Why does it continue? We like gadgets, and we're willing to spend a significant amount of our expendable income, not only in Iowa, but around the world, on electronic gadgets. It's the challenge of people in this room to create even more electronic gadgets that people would want in the future that are even more interesting than televisions and smartphones and video games and so forth. Semiconductor sales do not include the sales of the systems in which they are installed. And this is a much bigger market. So this is just the cost of the sales, of the components that go into the electronic systems. Let's look at how it compares to Iowa-centric commodities. What are Iowa-centric commodities? What are the commodities that Iowa is best known for? corn and soybeans. How many people have a farm background or rural background? Anybody here? Don't be ashamed. I grew up on a farm and spent a lot of time riding a tractor. In fact, until a few years ago, I spent more hours sitting on a tractor than I did in front of a classroom. So, how many people again have a farm background? One. Several people. So everybody knows a little bit about corn and beans. So we're looking at Iowa here, kind of a small state on area-wise and population-wise. In the U.S., Iowa ranks first in corn production, first in soybean production. I think these figures are still current. We kind of bounce around a little bit in a couple of areas. First in egg production, first in hog production, second in red meat production. So Iowa is big on agricultural commodities. If you drive around Iowa in the summer, you'll see cornfields and bean fields all over the state. And here's what the corn and the beans look like. Well, corn production in Iowa is around 2 billion bushels a year. In the United States, it's around 12 billion bushels a year. In the world, it's around 25 billion bushels a year. Soybean production in Iowa, about 300,000 billion bushels a year. In the world, about 8 billion bushels a year. Okay, so that's the commodities. If you looked at January 5th, closing markets in Boone, Iowa, closest grain terminal to where we're sitting right now, corn was selling for $3.14 a bushel, and soybeans for $8.93 a bushel. So let's see what the value is of the commodities that feed the people in the world. Value of the corn in Iowa is about $7 billion. In the United States, it's about $38 billion. In the world, assuming the price is the same as it is here in Iowa, it's about $72 billion. And soybeans, they're worth about the same on a worldwide basis. Total volume is less, but the value of the commodity is somewhat higher. If you look at 2017 semiconductor sales of $380 billion, that's about 3 times the total value of all the corn and all the beans that's produced in the world. We value electronics more than we value the corn and the beans that feed us. Semiconductor sales have averaged about 300% larger than the total value of corn and beans for most of the past 2 decades. Okay. So how does it compare to Iowa-centric commodities? Basically a lot larger than the major agricultural commodities. The semiconductor is one of the largest sectors of the world economy. And as we stated earlier, it continues to grow. This slide's a bit dated, but this ranks the size of the different semiconductor companies in the world. We see Intel and Samsung and Qualcomm as the major or the big companies in the area. Texas Instruments, we have quite a bit of interactions with, is 7th on the list. Broadcom, which was recently acquired, is about 8th on the list, and so forth. You'll notice that the country of origin of the semiconductor companies has a strong presence in the United States. If you look at the amount of money that's spent on R&D, and of course R&D money is usually spent on engineering salaries, or a big chunk of it on engineering salaries, we see that Intel spends about 22% of sales on R&D. So they have a lot of sales, but they employ a lot of people to make these products. Some other companies may have a little bit less. Samsung was only at 8%. Others are somewhat higher than Intel. If you look at where electronic devices are applied, communication systems, computing systems, instrumentation control, signal processing, biomedical, automotive, entertainment, military, and many, many more places that we use these types of devices. If you look at these different application areas, a lot of our electronic gadgets or systems will involve several different classes of applications here. If you look at the number of transistors in one integrated circuit, we're up to somewhere close to 10 billion transistors in some of the larger integrated circuits today. Close to 10 billion transistors in some of the larger integrated circuits today. It's oftentimes the case that the electronics circuit designer has to know or understand the systems that their products go in, oftentimes better than the customer. I know a lot of people at work, or several people at work, in biomedical applications, pacemakers. If they sit down and talk about how a heart operates and what the signals that are generated to control the heart, they probably know much more about how the heart operates than the cardiologists do. If you look at a circuit designer that's designing a control system that goes in a transmission for large construction equipment, they probably understand how that transmission operates as well as or better than the people that are designing the transmission. Okay. So we don't just work on electronics, we have to understand very well the systems that those electronic components go in. Because we can design a circuit that has certain specifications, but if the system that it goes into doesn't work correctly, there is no market. We might ask the question, how do engineers work in the semiconductor industry get rewarded? IEEE does a salary survey every year, and they break the salaries down by areas. Solid state devices, signal processing, electronics, microelectronics, power and energy, communications, control, and so forth. If you look at, any ideas how the average salaries of people working, engineers working in these different areas would compare? Think there's much difference? Well, according to the IEEE salary survey, the top of the list is those people that work in the electronics and solid state devices area. Of these areas, anybody know which one's at the bottom of the list? What? Power and energy are at the bottom of the list. If you look at the difference, the solid state devices people are around 150,000 average salary. The power, energy and power people are around 116,000. Is that difference significant? Yeah, it's what it is. Oh, automotive, we had that one list of one of the areas. If I look at an automobile, I used to think of an automobile as basically being a chassis, a motor, a drivetrain, and so forth. And I didn't really think of an automobile as an electronic gadget. Today, electronics accounts for about 40% of automotive production costs. And that percent will increase a lot in the future. So when you see an automobile driving down the road, it's really become an electronic gadget, or is becoming an electronic gadget. Okay. I'd like to give an example of a application that you guys probably have some familiarity with, to get some appreciation for some of the challenges that might exist. How many people have UHD televisions? Everybody, how many people have UHD televisions? 4K, it's another name for it. You're the only one? Oh, come on, there's gotta be more. Pretty nice, aren't they? Does anybody have 8K UHD TVs yet? Anybody here have an 8K? Okay, so 4K are pretty common. You go into Best Buy or Costco or wherever you buy your TVs, and the 4K UHD TVs are pretty much the higher end of the spectrum. Not all that expected, not all that expensive. Frame size of the 4K UHDs are 3840 by 2160 pixels. That's one frame. The frame rate is 120 frames per second. The pixel resolution, I'm not sure I've got this right. There's 12 bits RGB, and I'm not sure what alpha, what the resolution is on alpha. So I think there's about 48 bits per pixel. There's 36 for RGB, and then I didn't see what the specification was for alpha. The raw, uncompressed video data requirements are 3840 times 2160 pixels times 120 frames per second times 48 bits per pixel, which is 48 gigabits per second that we need for this 4K TV signal. Does anybody get UHD on their cell phone? You have UHD on your cell phone? Yeah. Pretty nice display. And okay. So the raw uncompressed video requirements are 48 gigabits per second. Some places say it's 36. So that's, I might not have this alpha right. I'm not sure exactly what it is, but let's not worry about the difference between 36 and 48. And if you go to 8K, which is just coming online, it's at 144 gigabits per second. 144 gigabits per second. If you look at audio, high-end audio is 192 kilosamples per second. 44.1 kilosamples per second is probably more common. Resolution is up to 24 bits. Number of channels is 2 if you have stereo. So the raw uncompressed audio data requirements are 192 kilobits per second times 24 bits resolution times 2 channels, 9.2 megabits per second. If you compare the audio data rate compared to the video data rate, what do we see? A lot less. Audio is almost free relative to the video. There's about a 5,000x difference between the raw audio and the raw video data rates. Are raw video data rates too large to be practical? If you're getting a 4K UHD signal on your smartphone, is that too big to be practical? Any ideas? Be careful what you ask for because we can probably provide it. So let's ask the question, how much would it cost to download a 2-hour UHD TV movie using raw audio and video on a Verizon smartphone today? This is a Verizon smartphone. And I did this calculation 2 years ago. And we'll adjust it a bit. So for data over 12 gigs in a month, Verizon charged $3.50 per gigabyte. If we have a 48 gigabit per second requirement for the video and a 9.2 megabit per second requirement for the audio, The total number of bits that are required then is we add these two together and then multiply it by 120 minutes. And that is 346,000 gigabits of data that are required. Oh, but they don't sell it by the bit, they sell it by the byte. So we have to divide by 8 to get the number of bytes that we need for that UHD TV signal. 43,000 gigabytes of data. How many people think they're getting 4K UHD video on their phones today? Or close to it. Let's see what it costs to get this. So it takes 43,000 gigabytes of data. And Verizon charges us how much? $3.50 per gigabyte. So the total cost for that one uncompressed movie is $150,000. You better really want that movie. Do you think you get anywhere near 4K UHD signals on your smartphone when you're streaming video? Not even close. If you tether your TV and stream that movie and go to the 4K UHD TV, do you think you're going to be getting the true 4K UHD quality? No, the data rate's the same, whether you tether it or whether you stream it directly onto your phone. So moving audio and video data is still expensive and still challenging. Be careful about what you ask for, because we can provide it if you're willing to pay for it. Well, what can we do to reduce these costs? Just tell Verizon to adjust their rates, right? They're probably not too willing to do that. But we don't have to transmit raw data. What do we do to reduce the data that we transmit? Compress it. We lose a little information maybe by compressing it. How much do we compress it? If you compress it too much, it doesn't look like you want it to look, right? So your video quality or your audio quality would change. We're not going to worry about audio because it's almost free relative to video. Any idea how much we can compress our video images? So when you go to JPEGs and stuff like that, those are compressed, right? And they've been working for years on compression strategies to still maintain reasonably good video quality. I believe the state of the art is about 14:1. So we don't have to have this really high data rate. We can reduce it by about a factor of 14. But even with compression, the amount of data that must be processed and stored is still pretty large. And the cost of transmitting even that compressed data is still pretty large. So instead of having $150,000 costs, we can divide the 43,000 gigabytes by 14. We only need 3,070 gigabytes of data. And consequently, the cost of that 4K UHD stream is only $10,700. What else can we do? What else can we do? What else do we do? What do we do? Yes?
Increase the amount of bytes that can be processed per second.
That's right, but we still have to transmit those bytes. And those bytes are still charged for us by the carriers. What do we do?
Back to Wi-Fi.
What? Well, that's a good idea. But that gets you to the access point. You gotta get the data to the access point. So you're just pushing you're pushing a bubble around. What do we do? Yes?
Improve download rates, improve the process.
We can improve the rates, but they still charge us per byte. And that number, they're not willing to change very much, I don't think. What do? We accept something that's much lower quality than what we're asking for. Because we can't afford to pay for what we might ask for. Does that make sense? And that means you don't really get this really high resolution. Still looks pretty good, doesn't it? But you don't really stream that high resolution image that your TV is capable of displaying. Let's compare things to what's happened in the last couple of years. The Verizon data plan of August 2015 was $7.50 per gigabyte. It dropped. It was $15 per gigabyte in 2014. It was $7.50 per gigabyte in 2015. I thought I had today's figure. Whoops. Today, any idea what it is today? If you want more data on a Verizon plan, I checked this morning. I think that on their standard plan, their unlimited data plan, you get, I think it's 15 gigabytes of data in a month. And then you can do a boost for another 5 gigs for, I think, $35. and they won't let you boost it past that. What do you want to do if you, what do they do if you try to go over that? What do they do? Slow it down. That's a polite word for the word throttle. Do they throttle it very much? Yeah, I was using my phone as a hotspot, and they say, well, they'll throttle to some level maximum. The level they throttle to is oftentimes so low you can't even keep a VPN connection going. So, some challenge to you as engineers and future engineers: become aware of how technology operates. Identify opportunities where electronics technology can be applied. Ask questions about how things operate and why. I think it's really important. I think that this data transmission thing that we looked at, which is really a key part of electronics, is probably an indication that most of society is really not aware of what the costs are of moving data around. Still an expensive proposition. I'd like to look at a few selected trends in microprocessors, DRAMs, and FPGAs. If you look at microprocessors, the first microprocessor was introduced in 1971, and it had 2,300 transistors. It was an Intel 4004. It was built in a 10 micron process. We'll talk about the feature size of the process a little bit later. If you look at the Pentium processors, the Pentium 2s, the Pentium 3s, that were around the year 2000, they were around 9 or 10 million transistors. And the feature size had dropped from 10 microns down to about 0.25 microns. If you look at the 8-core Xeon processor, it has about 2.3 billion processors, and that was in a 45 nanometer process. It came out about 8 years ago. GPUs, there are several billion transistors in the GPUs. The FPGAs are some of the highest transistor count devices They have close to 10 billion transistors today, and they're probably in 10 nanometer processes, as are some of the more current processors. Today, we might have something like a quad-core i7 processor, clock frequency around 3.4 gigahertz. This one happens to be in a 32 nanometer process, although they do have some now coming out around 10 nanometers, I believe. Power dissipation on this is 95 watts. That's just a number, right? 95 watts. They also have low power versions. And this low power version is about 5 watts. Doesn't have as much speed, doesn't have as much computing capability, but when you go to mobile applications and you're battery operated, there's a big pressure to try to reduce the power dissipation. Oh, there's a term you'll see referred to occasionally that Intel uses. They call it the tick-tock approach. So if they come out with a new processor, they'll have the tick version of it, which would be the first version. They'll have a design team that's working on the second version of that long before the first version is introduced to try to improve the performance. So that's the TOC version of the processor. Skyline processor, 14 nanometer CMOS process, about 4 gigahertz clock speed. And these processors, according to Intel, the price is around $350 for one of these chips. This is a wafer, and on the wafer you see a whole bunch of individual integrated circuits. And well, you can get an idea how big a wafer is because that's a person's head holding this wafer. At $350 a piece, there's quite a few ICs on there. The selling price for the components that are on that is a lot of money. I have a student that's working at Intel, and she said her husband works in processing, and he was told that if he drops a wafer, he'll get fired. Now I don't know if that's true or not, but at least that's that conveys the message that you can't afford to drop these things. We're out of time. Are there any questions? When you come to class on Wednesday, I request that you take a seat that you're comfortable sitting in for an extended period of time. I will take attendance by looking for seats that are not occupied. And I'd like to start in the front. Actually, if you look at the grades usually are highest in the front and typically drop towards the back. So we'll try to fill the room up from the front towards the back for 30 minutes. That's what we do.